All right, it's 4 o'clock. So let's get started soon. Um, all right, well, welcome everyone to lecture 22 in this class. So CS 545, Introduction to Robotics. And today's subject is on reinforcement learning, which, I mean, these days tend to be very popular topics. So hopefully this lecture will give you a good overview and foundation into reinforcement learning. So a couple of logistical things. So homework 3 was due April 1st. You might still be working on it, especially if you have late days, but if you've run out of late days, we cannot accept any homework after that. Labs 3 and 4 have been released, so try to work with your team to see how far you get, and then see all the details about using the physical robots on Piazza. So one of the TAs, Shihan, had a procedure set up so that you can sign up and then use the robot. And we are working on homework 4, so I'll try to make sure I'll try to release it maybe tomorrow, and then it'll be based on material mostly from next Monday's class, but it will also be a little bit related to today's material as well. Any logistical questions? So normally I have the Google Doc where students can type in questions, but in practice, no one has been using that. So if you want me to still use it, then send me a message on Piazza after class, and then I'll continue using it. Usually people type it in if there are more people in the room, because then they prefer being a little more anonymous. But in a smaller classroom, then students tend to get more comfortable asking questions, the usual way. All right, so if there's no other questions about this, let's dive into the technical material for today. All right, so today is about reinforcement learning. And when we talk about this, we're going to assume this framework where we have some agent. So you can think of the agent as a robot. I mean, some people call it agent because agent can be something like a human or something that might not be a robot. So sometimes people just use agent, but for this class, you can think of it as like a robot. So you have some agent, it interacts with some environment. So that's a term that we've used before. So we talked about, the environment, which includes things like, not just the robot, but also objects in front of it. And I mean, the notion of what is an environment is subjective. I mean, it depends on your task. Like if your task is doing some bin picking in a robot warehouse, like if you're working in Amazon, they have, robot arm, or I guess maybe a covariant or AMB robotics. There's other companies that do, robot arm, then the environment would be like the robot arm, the box or bin of objects in front of it, and then the object. So that would be like the environment here. Now, in reinforcement learning, we assume that the agent can take action. So the notation that we use is A for action. So if you remember the Bayes filtering from earlier, we were using U as the control. It's basically the same thing, all right? But most people who do reinforcement learning use the A notation for action. Some other robotics, people like control, they might use U. So just be aware of that notation thing. Now, what we have is the environment is where the agent or robot takes action, and then it gets feedback. So the environment will give us the reward. And this is one of the main new things in reinforcement learning. You get a single scalar reward after each action has been executed. And then the agent will move to the next state while also getting that scalar reward signal. And then the process repeats. So, the agent goes in a cycle of take action, the environment will produce the next step, and then you get the next reward. You get the reward. And the objective is for the agent to learn to act so as to maximize the expected reward, or maximize the expected sum of rewards. And all the learning here is based on observed samples of outcomes. So in the most basic framework, the only way to get samples is to actually take an action in the environment and then get feedback. I mean, there's variants of that, like, offline reinforcement learning, but the most basic variant is the agent has to take some action in the environment, get an observed sample, then it must figure out what to do from that. And it might have to do this a lot. So if you're familiar with things like deep reinforcement learning, that stuff might have to repeat a long time. And it might be bounded by how much compute you have. So yeah, that's the framework that we will operate in for today's lecture. So reinforcement learning has been used in many different scenarios. So one example, and this is from Peter Stone's lab at the University of Texas, Austin. So they have this robot, like this robot dog. I think it's a dog. And then they were trying to use reinforcement learning to train it to walk. And I assume what they did was, the robot starts in some position and then it's rewarded based on how far it goes in front of it. Yeah. And the further it goes, the higher reward it gets. And if you want some videos, like this might be near the beginning of training where, the robot is trying to move forward, but we see that, it's moving a little bit forward, but it also doesn't seem, it seems a little bit slow. And of course, this video is also probably like sped up a little bit. I don't know for sure, but yeah, but you see that it was making some progress. And in fact, if you've worked with real robots before, this is actually a lot more than you would expect to see from initial training. And then during training, it might look something like this. Loading. Oh, there we go. So if you compare this with the video from the last slide, it seemed like it's a little bit quicker, like it's a little more systematic in how it moves. Its legs is a little bit more unified and a little bit less sloppy. So the way to think about that is this is just like some snapshot of training. Like training must have happened over many, many iterations, and then they just took a video from like maybe halfway through training. And at the very end, it might look like this. Loading. And this is what it looks like at the end. It looks pretty similar to the last video. So maybe the last video was showing something that was close to convergence. And that was from 2004, and then these days there's many more examples of reinforcement learning successes, and then there's also variants like reinforcement learning from human feedback, which power things like ChatGPT and other generative AI things that people are thinking a lot about today. Yeah. All right. So when we study reinforcement learning, we are still assuming that we're in the Markov decision process framework. So we covered Markov decision processes in a prior lecture, but just to review it, it is a framework that consists of a couple of components. So the first is a set of state, right? So a state is like some configuration of the object and the robot in the environment, right? And then usually you can have many different, if not infinite in many different states to consider. There will be a set of actions per state, so they might be state dependent, or maybe they might not be, but there will be some action that the robot or an agent could take. There is some transition probability. So we use the T notation, so T SAS prime here, this is the same as the probability of like xt plus 1 given xt and ut that we covered when we were talking about the Bayes filters and stuff like that's basically the same thing here, just different notation. And then we have a reward function. So could be a function of the current state as well as the action and the next state, or it might not be a function of some of these. So it is very flexible. Now, the objective here is we are still looking for a policy. So the point of reinforcement learning is we have some robot operating in some environment, but we have to come up with a way to tell it, what is good and what is bad. And then somehow it's got to do something to, increase the expected reward that it gets. So in reinforcement learning, in contrast to the prior lecture on Markov decision processes, we don't know the model and we don't know the reward function. So we don't have access to that information directly, which means the agent must actually try out action and state to learn like what is good and what is bad. Now, the model and the reward function still exist. It's just that the agent cannot actually access them. So it can't run something like value iteration directly because value iteration, you assume that you could write out the formula, T, state action next state. You assume that you could write out like what is this function. But here we don't assume those functions, but we get access to a sample of them. So yeah, so if you remember this 3-car Markov decision process, like we had cool, we had warm, and then you had dehydrated. And then we just assume we don't have access to T and R. Yeah. All right, any questions on the assumptions here? All right. Hi, so offline MDP versus online RL. So if you were trying to study an offline solution, then your robot, you would have some robot or agent and some Markov decision process. You would know like what is the transition probability, what is the reward function. So if an agent is here, then a solution like value iteration where we're trying to compute what is the value of a given state, assuming that we follow the policy and then assuming that we act optimally from that state, which is the optimal value of a given state. Or if you remember the notation, we use B pi. So that's the value, assuming we follow that policy pi. So like the value is the expected sum of discounted reward starting from that state, and then we follow that policy. And then when you're doing value iteration, you would need to know like what are the transition probabilities. Like if the robot here said, what happened if it moved in, I guess in this direction, it must know like what's gonna happen. And then presumably it knows that it might get a very negative reward because this is some fire or lava pit. But then if you have online learning, then you don't have access to that. So at some point, the agent would have no choice but to try out things. Yeah. So this is why RL is normally used in simulation for obvious reasons. Yeah. All right. So there are different types of reinforcement learning algorithms. So a very common separation of reinforcement learning algorithm is model-based versus model-free. Now, when you think about this, remember that whenever I say, we can divide up these algorithms into this category and that category, and very often the lines are very blurry. Like you can have an algorithm which is arguably both model-based and model-free in some sense, like maybe it uses both of the components somehow, but this just think of this for now as like separate algorithm. It makes things a little bit easier to when you're getting started with this. Yeah. So I guess the idea conveyed here is like model-based mean we have a model of the environment somehow. Like that's the core thing here. You build some model of the environment. And in model 3, we don't assume that. And you remember, like, what do we mean when I say what is a model here? Like that is referring to the the transition. So if you remember what a model is here, we have a model like T, state, action, next state as input. Like this is the model. Yeah. Yeah. So here's the idea. Learn an approximate model based on the experiences that the agent got when it was, running in the environment. Then solve for the value, like maybe do value iteration as if the learned model was correct. That's it. Like that's basically the 2 bullet point summary of what model-based means here. So step 1 means learn an empirical MDP model. So whenever the robot is in some state and then it's taken an action, it'll run that, and then the environment will produce the next state. And then you can do that many times, and then you'll learn, what is the probability of being in some next state, given that the robot was originally at state S and took action A. And this will give an estimate of T. So we have T hat because hat in math notation usually means an estimate of something. So, like a hat of T here. And you can do the same thing with the reward. Every time you get a reward, then have your approximate reward function, and then you approximate that. Yeah, and then you solve it, and use some technique that assumes access to the transition T and the reward R, and then just solve it as if they were correct. Now, the solution to that will, of course, depend on how good your empirical estimates are. Like if they're approximately, if they're pretty good, then it's probably okay. If they're very off, then in practice, step 2 probably won't work very well. So this is a very straightforward, framework to use in reinforcement learning. All right, is that clear? Yeah, question?
A transition for a new state.
So are you asking what is the output of TSAS prime? So this thing is it's a probability. So it's a probability. Let's just write it out another way. Well, yeah, I guess maybe this is easier. So this is just a probability of next state given current state in action. So this thing must be like, if you're in a discrete land, then it must be between 0 and 1. So this is not the next state, it's a probability of the next state. Yeah. That's that. Yeah, question?
You repeat that piece a little louder. Does the reward function only see?
So the question is, does the reward function always need these 3 components, basically? And I should also say, when we talk about the previous state, that's not part of the input. So the way to think about this is, this S here is the current state. So the previous one is like before that. So it's actually not part of this. So it's the same with T. So This is current. Current state. Yeah, so that's the current state, this is the next state. And this is the action taken at the current state. So let's write this. Yeah. Yeah, hopefully the board is easy to read back there. All right, any other notation or other questions about that? All right. All right, let's do an example. So we're going to be considering some simple grid world examples, because in grid world, you can explain things in a slide. And everything is discrete, so you can enumerate like, states and actions. In general, that might be difficult, but in grid world, you can make that assumption. All right, so we have this grid world thing. There's five states that the agent can be in, like A, B, C, D, E. We're going to assume a discount factor of 1. So remember, the discount is how much do we multiply the future reward? Usually it's 0.9 or something, but we're going to make it 1 to make the calculation simpler. And then when the agent is at A or D, the only action is exit. But if it's in B, C, and E, then it can move. Well, I guess there's only one place it can move, but in C, it could move upper to the right. Yeah. So let's say that we run the agent in the environment. So when we talk about running the agent in the environment, what we really mean is that we have a set of episodes. So one episode means the agent is at the start state, it executes action, and then it finishes. And that's one episode, right? And here we just did 4 episodes. Now, all the episodes, they're only in 3 time steps because we have a very simple MDP here. So like episode 1 means the agent starts at B, it moves east, lands in C, it moves east, lands in D, and then it exits. The same thing for the other episode. Oh, well, at least, same thing subject to like different, states in action, but the same principle applies. All right, and then let's do the most naive thing by approximating the learned model, the transition and the reward, just from the empirical estimate. So let's look at the transition from B east C here. So why is this approximate? Why is this empirical model 1 here? So do you remember what this means? Yeah, maybe the arrows are confusing here. Let me make it cleaner. But everyone see why this is 1, right? Right? Because every time the agent is in B and moves east, it lands in C with probability 1 empirically. Like we never see any B east and then something other than C, which makes sense because the agent is here, it can only go here. It assumed that the agent never did like a no-op and landed in the same spot. No, but we never saw that. So our learned model is just gonna assume that we didn't see that. What about the reward? Like why is this term -1 here? R B east C? Why is this -1? Or at least, but why, like, can someone explain, like, why do these terms appear? Yeah. All right, so B east C, you get -1. B east C, you get -1 again. And it doesn't appear here, so you get -1. That's the only, it's the average of -1 and -1, basically. If you're at D, exit, and X, you get +10, +10, +10, and it doesn't appear here. So the average of 10, 10, 10 is 10. All right, that's our learned model. So any questions? Because this is basically model-based learning. All right. So another example of model-based versus model-free distinction is conveyed in the problem here. So if you want to compute the expected age of CS 545 students, then if we knew the if A was this, if A was like this random variable that had the age, and then we knew the exact, if we knew this probability exactly, then we could run the definition of what is the expected value, right? It might be 0.35 times 20 if the probability of someone age 20 is, no, 35%. That might be an accurate probability. But if you don't have access to the true probability distribution, then you can approximate it with samples. So you get A1, A2, and AN. So A1 would be the age of someone in this class. No, I don't want to point the name, but just imagine that A1 is like someone here, then A2 is someone else. So trying to compute the expected age in a model-based way would look something like this. You try to compute an empirical estimate of that probability distribution, just like how we were trying to get an empirical estimate of the T and P here. And then your expected age is just this thing here is an approximation because P is just an approximation, but this will give you an expected value for the age in a pretty reasonable manner, right? And if we have enough data points, then eventually we'll learn the right model, right? Now, computing the age in a model-free way would look something like this. Again, we don't know what the true probability of A is, so we just directly estimate the sample like that. Anytime we have n samples, just take an average of that, and then that is our estimate. Because samples appear with the right frequency. Right. So this is model-based versus model-free in a very simple setting, which doesn't even involve reinforcement learning. And they'll compute the same thing, but you can see that they do it in a slightly different way. So. All right, so we talked about model-based learning in a few minutes, and then now we'll talk about model-free learning. And then when we talk about model-free learning, we have another taxonomy, like we have different types of algorithms. Again, you can think of them as having a lot of overlap in some sense, but for the sake of explaining things, we just assume that there are distinct types of algorithms and approaches. So one of them is like a sort of like a passive reinforcement learning. So you can kind of see that what happened is, like it, you probably know that there's a distinction between passive and active. Then we'll go through what these mean. So in passive reinforcement learning, the simplified task is policy evaluation, right? So the input is going to be some fixed policy pi. And we don't know the transition, and we don't know the reward. And the goal is to learn the state value. Now, I think the wording of passive and active, it can be a little misleading. The passive does not mean the agent does not take action. Passive refers to how there's no choice about what action to take. But normally you would think of passive as like not doing anything, but here where the agent has to do something, it just doesn't have a choice about what it is doing. But then later, when we talk about like active reinforcement learning, then there will be a choice about what action the agent should take, because some action will be better than other, and like exploring unknown region of the environment. So in this problem statement, the goal is to learn the state value. And what the learner does is there's a fixed policy, just execute it, and then learn from the experience, which means learning the state value. Yeah. Again, the state values are, what's the expected sum of discounted reward if the agent is at some current state following its policy and follows its policy. So one way to do that is to do direct evaluation. So compute the value for each state under the policy. And then whenever you see a set of observed samples and write down what the sum of discounted rewards turned out to be, and then average those samples. Because again, the second bullet point, that sum of discounted reward, that's what it really means to compute a value. Yeah. All right, so let's do an example of direct evaluation. So remember that here we have to write down what the sum of discounted reward turned out to be. And again, the gamma is 1 to make the calculation simpler. So you know the input policy. You observe a few episodes during training. All right, episode 1. This might actually be the same as the prior example. So episode 1 is agent is in B, it moves east, lands in C, gets reward -1. Then it moves east again, lands in D, gets reward of -1, and then from D it exits, and then gets +10. And the X here represents the fact that there's no next state after that termination state. And then you can do the same thing again for the different episodes. And then what is the output like? So what does direct evaluation actually compute now? So what should happen is that at every single state, it should try to compute the average of the sum of discounted rewards based on the averaging the sample that it saw. So let's look at some examples. Let's look at -10. So -10 must be the expected sum of discounted reward if the agent was at that date and then follow the policy. That's the definition. So why is it minus 10? Well, there's only one case when it was actually at A, right? In this episode, the only action it took was exit, and then it was immediately over. It got an award of minus 10. And so it gets 10 here. Same thing for plus 10 here. So now the interesting thing here is, yeah, how do you get like plus A plus 4 or minus 2? Now I'll give you a couple seconds to think about that. But so who can tell me like why does B result in plus 8 as the estimate of the expected sum of discounted rewards if the agent is at that date and then acts according to its policy? Why is it plus 8? Yeah, what?
Average of -1 plus 10 with that for one. And -1 plus
The So you're averaging, how many things are you averaging over?
the whole episode 1.
The whole episode 1.
-1.
Yeah. So you have -1. All right, here you have -1, -1, and 10, right? So what do you do with those? Yeah. So when you're at B, the instantaneous reward is -1, and then the next time step, the instantaneous reward is -1, and then it's plus 10, and then you sum them up, you get 8. So we have no discount because the discount is 1. If the discount were like 0.9, then you would have to multiply -1 by like gamma, and then 10 by gamma squared, right? So you would have to, like, if gamma was 0.9, you would have to downweight those other states, but we made it just 1 so that you didn't have to do that. Final exam, you will. So you get plus 8 here. Now what happens here? You also get a plus 8. So the average of 8 and 8 is 8. What about -2? So if we're in episode 3, we start at E. The rewards we get are -1, and then we get -1, and then we get plus 10. That's 8, right? If we're in episode 4, we get -1 reward plus -1 plus -10, which is -12. So what's the average of -12 and 8? That is -4 or -2. Everything clear? Yeah. So yeah, like this is the more interesting example because you start with E, but then one episode you got like one episode you got plus 8, the other episode you got -12. So you got different rewards, even though you started at the same state. So that's why each of these episodes is like a sample, then you average them together. Right? Yeah.
Could you please also explain how we can get +4 on C, right?
Oh, +4 on, all right, how do you get +4 on C? All right. Episode 1. You're starting at C, you get -1. You go to D, then you exit, you get +10. So that sample is +9. Episode 2, it looks the same. You get a sample of +9. Episode 3 is the same again. You get +9. Episode 4 is finally where things get different. At C, you get -1 and then you get -10. So that's -11. Well, so what's the average of 9, 9, 9, -11? So the way I mentally calculated is 9 plus 9 plus 9 is 27, -11 is 16. You divide it by 4 because there's 4 samples here. Then you get +4. Right? What's the problem with this thing? But yeah, there's some questions here. So what's the question?
So what we're gonna do, just pick the start point and add all the numbers together. Yeah.
Yeah, you compute the value per episode starting from the indicated state, like the state that you're interested in. You start from that when you do the sum, and then you do that for all the different episodes, and then you average them together. Yeah.
Just to do a further clarification, if the data right here is not 1, and when you calculate the +4, another value on C right there, so it should be -1 times gamma and +10 times gamma square, or just only one yeah.
I think this is a conversation we should have offline. Like it's probably gonna get a little bit detailed in the calculation. So we're gonna have our break in a few minutes, so we can talk about that. Yeah, the question. Oh yeah, the output value is here. The sum of discounted reward. Well, I guess what those values mean are, they're valued for each state under the policy pi, which is the sum of discounted reward for the agent if it's at that state and then follow this policy. Yeah, and it's expected sum of discounted reward, but in the example, we set gamma to be 1, so there's no real discount, just to make the math easier. Yeah. Yeah, so that's what these values mean. So what's good about direct evaluation? Well, it's easy to understand. I mean, I know there were questions here, but the questions here were good, but I guess relatively speaking, direct evaluation is easier to think about. And it doesn't require knowledge of the transition probabilities and then the reward function, and it eventually computes the correct average value just using the sample transition. Because if you get enough samples, it'll converge to the right thing. So what's bad about it? I mean, the top half of it said what's good about it. So the bottom half should say what's bad about it. All right, what's bad about it is it wastes information about state connections. So it seems like if you have two states and they're very close to each other, then in some sense their values should probably be similar. I mean, each state must be learned separately. So we computed these, but they were all like separate. Like there's one calculation for A, one calculation for B, and so on. So it takes a long time to learn. Does everyone see what I mean by the first sub bullet point here? Like, think about it. If B and E both go to C under this policy, then, and also if their rewards for going from B to C and from E to C are the same, then it seemed like they got to the same state. So their values should be pretty close to each other. But in fact, what we see is B gets +8 and E gets -2. That seems pretty divergent. Now, eventually with enough sample, you'll converge to the true values, and then so the numbers here will become the same, but it just might take a long time. And a very important principle is that when we have different algorithms that compute the value, we prefer the one that is more sample efficient, the one that relies on fewer numbers of data points. So why not use policy evaluation? So remember what we were talking about earlier, where we had this diagram that showed the visualization of here's the current state. The circle represents the fact that the robot has committed to an action, but it hasn't resolved it in the environment. So like you've committed the action, but if you're using code, you haven't run like environment.step with that action. And then you get your next state, and then the transition, the tuple is state, action, next state. Now, so again, you could try to compute the value for a given state based on a value iteration like update. So you get your value with no time steps left under pi. So with no time steps left, there's nothing left to get, though. That's the base case, you get 0. This is like the recursive case for k equals 0. So you get the next value based on the sample here, the probability here multiplied by the sample value. So that's the instantaneous reward plus the discount times the value here. So the main issue is, again, remember that we're assuming that we do not have access to T and R, which I should also say the very reasonable assumption. Like if you know exactly the transition probability, then that's a very strong assumption. Like if you have a robot arm that's trying to grasp different objects, the transition probability would need to say, here's the object, the robot, here's the action. It must tell you the probability of the next state. And if it's handling, if it's in a very cluttered environment like that, transition probability is going to be very hard to get. So it's a very strong assumption to assume that we have T here. And same thing for R. So yeah. And the key question here is, how do we do this update to V without knowing T and R? So I think this is a good time to take a break, because right now we're going to be discussing some sample-based algorithm for computing the value. So let's take about a 5-minute break here, and then we'll come back at around 4:55. All right. I'm happy to answer any questions during the break too, if you want. Oh, you have a question? Okay. Let's take a look at the.
If we just assume the gamma right here is 4.8, so how can we calculate the C right here? Because if the gamma is 0.1, we can write the formula like this.
I'll write it out. We can do it. We can do it.
Okay.
Let's do it here so that people can.
Okay.
Everyone can. Actually, wait. Do you want your?
Yeah, that's fine.
Actually, let me turn off my.
No.
Like we.
All right.
I don't want to in the video. So. Let me see what you want to do. It's like the average of a bunch of things. Episode one is -1, plus 5. So if -1, and then you get a +10, which you discount to 8. Yeah.
Oh.
And the same thing for 2 and 3, right?
Yeah.
This is 8, and then that's right, 7, 7. This one is get -1 plus 0.8. Now this is -10, so this is minus 8, right?
-9.
And then, yeah, then you would average, no. I guess we can just do like. Yeah. That would be 21 minus 9, which is 12, and then divided by 12, divide 9 into 3. Huh, interesting. Yeah.
So the key point is to pick the right start point and just look at all the episodes.
The right start point is pretty simple, like if you're including the value of C, that's your starting point.
Yeah.
So is it you're walking in a gamma? I love that. Yeah, he's assuming.
Yeah.
Yes, we want to know what happened to his right evaluation if you had,
What is the time to use like London square, London square, when it's time to use that?
oh, when you square it?
Yeah.
Oh, if you had more time. Because here, whenever the agent is at C,
Yeah.
there's only the instantaneous award here, and then the next time step, the next time step is the anchor one. So there's only 2 things left. Here.
So what is the highlight this square?
No, this is just, like, this is just one, like, this is.
But
here you started here, and you get the instantaneous awards, and then this will be gamma, then this is gamma. So if you have, but you need, no, you need another time step after this to do.
Oh, like from into C to D, so the C is like, we can use a gamma and the D is a gamma square. Yeah. Okay.
But this is why I use gamma is used.
Oh. So I gotta use it for.
Oh, yeah. Yeah, so we want to lecture about our composition in the positive.
Yeah.
So remember, we talked about like gamma is that means we in the future order that you get, and all like in theory, it's a principle about to weigh awards closer in the time horizon to be higher amount. Like it's better to have higher awards, the awards now than the same awards that later. And so if it's one step in the future, you multiply. You have a gamma, zeros have a different or gamma. The next one. So when we talk about expected sum of discounted reward, then that's what we mean by the discount here. This is the discount factor.
Thank you. Thank you.
Oh. All right, let's get back. I'll give you a couple of seconds to get settled. Everything okay there, guys? Yeah, yeah. Um, yeah. So we left off talking about things like direct evaluation, like trying to compute what the values mean for each state based on sample. Then we talked about some problem, and then this could help rectify the issue of like connection between states. Because if you're doing this type of value iteration, then you're taking into account the possible like next state in that sum here. And so you'll be able to make better connection between the values of different states. But this requires access to T and R, which we don't assume we have access to. We only have access to them like indirectly through sample. So we want to compute or improve our estimate of B by computing these averages. So this is, think of this as like, you're given some state, the agent has K plus 1 time steps left in the environment, and then the agent is following pi. So what's the expected sum of discounted reward if you're at state F and following that policy pi with this many time steps left? So the idea is to take samples of outcomes by actually taking depth in the environment and then averaging them. And what that means is you'll see that this is a weighting thing. It's like a probability weight. So for next states that are much more likely to happen, they have a much higher probability, and therefore they take up more of the weight in that sum. So one sample might be, the robot took a step in the environment, and then it got this instantaneous reward. So it doesn't know what define R, like it just got a single number. Like that's just what this is, just a single number, like 1 or 0, whatever. Plus this thing here, the discount times the value with K time steps left. Assuming that the agent is at the state, and then whenever we talk about the next state, again, we usually have the prime there. So do you see why this is one sample? Like this is your like a formula, but this is one sample that appears here. And with enough samples, we will eventually get, the average of them to, match what this probability means. So you have another sample, and then another sample, then you get n samples. And then you average them out. So this is okay, but one of the main issues is that we kind of assumed that the robot could start at some state, take an action, it went to the next state or successor state, we computed something, and then we just moved the robot back to the state and then did another action, and then, we're doing the same action here, but the probability, of course, could be stochastic. Like given the same state and the same action, it could have easily gotten to different next states. But the problem is, the agent can't sort of like rewind and then, execute again. Like in practice, in simulators, you can do that, but then it'd be a little bit cumbersome to keep trying to reset and then going back to a state. So there's a better way to do that. I guess this is like some like Oracle robot. Alright, that brings us to temporal difference learning. So this is a very fundamental topic in reinforcement learning, like very important. And the idea is that, we should learn from every experience that we get. So instead of computing all the samples, as we did in the last slide, and then averaging them to get the value for this given state, we should just learn from every sample as we go. Like we got sample one, we should learn from it right away instead of computing n samples, especially if we're going to be setting n to be like, a billion or whatever. So the idea that we update the value each time we get a transition. So transition would be state, action, next state, and the reward that we obtained. And yeah, if you read like papers in reinforcement learning, you'll see like this notation a lot, like S-A-R, S prime R, or some people put the R first, then the S prime. And again, the policy is still fixed, but we move the value for the value of whatever successor occurs. So temporal difference learning is like a running average. So we might have one sample of the value, and then we do an update like this. So we have some value. So this is the value of graph state S, and following pi, like the expected discounted sum of reward. We're going to assign that to be equal to 1 minus alpha times, the same thing plus alpha times the sample. And this is another way to think about the update. All right, so let's look at this formula here. So what happens if alpha is 1? If alpha is 1, then this term goes away, and the value is exactly the sample. That good? You should be saying no. Like if alpha is 1, is that good? Like what happens if alpha is 1? Like if alpha is 1, then each time we get a new sample, we're making the value exactly equal to that. That means we ignore and we throw away all the prior information. Well, that seems like a huge waste of samples. And then, the next time we get a sample, we're just going to override that value. But this value needs to account for all the possible samples. So in practice, alpha should be a small value, but it should be it should be non-zero, like greater than 0, but a small value, like 0.1 or 0.01 or something even smaller. But for some of these slides, we'll show alpha equals 1/2, which is really big, but that's mainly because it makes the math easier to think about. Yeah, but in practice, just think of alpha as like some very small value, because it should weigh the current sample, but it shouldn't throw away all the information that has been accumulated into this value estimate. All right, so does everyone see the difference between this and the prior slide where we talked about like we listed different samples, then we would average them together. Like this is different. We do an update immediately after we get each sample. And we should also talk about the moving average, because what we do here, this is a moving average. So I think most of you have seen like, what a moving average means. Every time you get a sample, you do some calculation that immediately like averages that sample into the prior computation. So an exponential moving average looks like this. If you have this type of interpolation update, So you have this thing is equal to 1 minus alpha times our prior estimate with n minus 1 sample plus alpha times the nth sample. So this bar is your estimate. It's like an average. It has information from all the prior samples up to now. And then xn is like one number that we need to include in our moving average. And again, you can, if you expand out the math and then you work it out, it ends up simplifying to this. So you have xn, which is like your exponential moving average up estimate of whatever thing is generating the sample. You have xn plus 1 minus alpha times xn minus 1 plus 1 minus alpha squared xn minus 2. So because alpha is between 0 and 1, and alpha should not be 1, covered earlier, then this sample contributes way more to the estimate here than anything later. And then same thing with this, like the more recent sample, like if you're at sample number n, the more recent sample of xn, it contributes the most, and then xn minus 1 contributes the next most, and so on. So this is what people mean when they talk about like moving averages and exponential moving averages. Yeah. And what it means is, you forget about the past. And the nice thing about this in reinforcement learning is that because our estimates were based on the instantaneous reward we got, plus the estimated value function, then because the estimated value function was bad originally, then it's actually good to discard it at some point. So yeah, and then you can change the value of alpha, like you can make it so that it decreases, and then therefore you get like the real average instead of a moving average. But in general, like I think people prefer down weighting and then eventually ignoring the older sample, because they end up just contributing less, and their functions of estimators that are usually wrong originally. So all right, temporal difference learning example. So this is an example for this. This is temporal difference learning. Right. We have the lambda, gamma is 1, but we have alpha is 1/2. That's huge, but we're going to make it 1/2 to make the math easier. So we're also going to assume that our current estimate for the value at this state is 8. That's just some function that we have seen, that we have computed maybe ahead of time. The agent starts here. The observed transitions are, if in B, it goes east, and then it gets -2 reward. Now, because we're in temporal difference learning, you can compute estimated value after each transition instead of like waiting until the end of an episode. And this is the update. And then therefore we get -1. I'll give you a second to think about that. This is the temporal difference update for that single transition. Right. You see why it's -1? That's important. So no, if this -1 is not clear, I can go through it. Yeah, what? Oh, okay, yeah. So when we do temporal difference learning, this this thing is the definition here. So this state is our current state. So the current state is B in that transition. We move east, we go to C, we get -2. So what appears here? This is -2. That's the instantaneous reward that we get. It's -2 plus gamma times the value at that successor state. And then we look at that, the value of C, that's 0. And so this is 2 plus 0, which is 2. Alpha is 1/2 to make the math easier. So oh, sorry, it's -2. So sorry, this is -2 because we have a -2 here. So this is -2 plus 0, so that's -2 multiplied by 1/2, that's -1. Now our current estimate was 0 because we had the estimate at 0, so it's 0 plus 1/2 times -2, which is -1. Yeah. Again, the big difference here is we observe a transition, we make an update immediately instead of waiting until the end of an episode to do that. All right. The next transition is the agent is in C, it goes to D, then the instantaneous reward is -2. All right, think about what number goes in here. There should be like one update here. So again, when we write this notation, C east D -2, C is the current state F. East is the action that's A, or like pi of F. And then D is the next state, so it'd be the successor, or S prime. And then -2 is this thing here. And then you get 3. Got it? All right, everyone clear on how to get 3, right? This is equally important compared to knowing how to get the -1. I can go through it, but if you don't want me to, I can skip to the next thing. Why don't I just do it anyway? I'll just do it anyway. So we're at C, we go east, we're in D, and then the instantaneous reward is -2. So we get -2 here. -2 plus gamma, that's 1, so we don't need to worry about that. -2 plus this thing, which is 8, because our value function is 8 at that point. So -2 plus 8 is 6. And then times alpha, which is 1/2, so you get 3. And then what is the prior estimate? Well, the prior estimate is 0. So this thing is 0, this is 1/2 times 6, which is 3. All right. Yeah. Instant reward, then the future reward. All right. So we talk about sort of like what is temporal difference value learning. Oh, sorry, this is a typo, it should be learning here. It's a model-free way to do policy evaluation. So you saw that we were mimicking the Bellman update with running sample averages. So the Bellman update, if you remember from the Markov decision process lecture, they were like how you define the values in terms of the values themselves. So what we mean by this bullet point is that whenever we turn the value to a new policy, then we always have to do this type of like an argmax over, like we have to do a max over value, so the tricky part when you try to do that, like if you remember the tricky part is whenever we try to get some policy from the value function, we had to do some sort of like a complicated max over all the possible actions. And so we talked last time about how it's much easier to define a policy if we just know the Q value directly. And the Q, like the Q's are the state action value instead of the state owned value. So learning the Q value in a temporal different way, that's one thing that insight was what powered a lot of modern reinforcement learning today. So the key idea is just to learn the Q values in a similar way as we learned the values using sample. Yeah. All right, and then yeah, that brings us to the active reinforcement learning. So this time the agent is actually going to have to take steps in the environment. Like it's not going to be given a policy, then ordered to follow it. It's actually going to have to choose what action to take. And then from the sample there, it'll have to learn, after every transition, how do we update the Q value? Right. So if you remember from earlier in the lecture, we talked about, the full reinforcement learning where we like, well, actually, no. So here, this is sort of like the full reinforcement learning problem. So the goal is, how do we learn the optimal policy? And then by doing that, we will also learn like what are the optimal values, because the policy is just like when you're computing Q values, the policy is just argmax of action that maximizes the Q value at that given state. And this is where we have the fundamental trade-off of exploration versus exploitation. And here the learner has to make choices instead of earlier in the class when we talked about the learner does not have a choice, it has to follow a pre-prescribed policy. And then this is what we implied a few slides ago about Q value and stuff. So if you remember from last week, value iteration is find the successive depth limited values. So start with the value for every state with no time step left, we get 0. Given the value with k time step left, calculate the value with k plus 1 time steps left. And this was the update that we talked about when we discussed value iteration. So, value with k plus 1 time step left there, you pick the max of the action, which is giving you the max value of this thing, which is the weighted sum of the transition multiplied by current instant reward plus the future reward. So the Q values are much more useful for more easily defining what a policy means. So if you start with Q with no time steps left, make that equal to 0, which we know is right, and then given QK, calculate the next Q value, which assume k plus 1 time steps left. Oh, and this is what the update looks like. So notice what changed here. So now the max, the max moved from here into here, right? Any questions on this equation? Because this equation is very fundamental. Like, in fact, this is a variant of this you often see in many reinforcement learning papers. So And again, the reason why you have a max here, the max of A prime is, well, first, this is different in general from the A here, right? So this A means you've already committed to that action, but this A prime is just an arbitrary action from all the possible actions. It could be the same as A, but in general, it's not. And then this is just going to find what is going to maximize this value here. Because we assume that if we have a Q value with about, calculate the Q value, assuming that you're acting optimally. And based on that, we can come up with a sample-based algorithm called Q-learning. So yeah, if you're familiar with things like deep Q-learning, then those are algorithms that have powered a lot of reinforcement learning updates. So this is just the vanilla, like most basic type of Q-learning algorithm that, powers a lot of current reinforcement learning algorithms. So the key idea is we want to do a sample-based Q-value iteration. This is sort of like the algebraic mathematical update, but in practice, what happens is agent is in some environment, it takes action, then it gets to the next state, also gets the reward, and we want to learn that immediately. So we don't want to just discard, just like wait until the end of an episode. We want to learn from that right away. And yeah, we remember that we were talking a lot about the grid world, where this is like some example of with some values of gamma and some other values of like what's the transition probability. But the main idea is like after some time you see that there are different values, like 4 for each state, because you have 4 actions for each state. And that's why there's 4 numbers here. Then you get the +1 if you're here, then the -1 if you're in like a fire pit. So in Q-learning, receive a sample, your state, action, next state, and the reward. We consider our old estimate. Consider the new sample estimate, which is reward plus gamma times the maximum of the Q value when you're at the successor state. We incorporate that into a running average, which looks like that. All right, that's Q-learning. All right, any questions? It's a very important algorithm in reinforcement learning. Yeah, so we'll look at an example, but just keep in mind that this is the update here. So let's look at an example of Q-learning. So what you see here is that this video, so I think it's from Peter Beal at Berkeley, where this is the agent. The agent is in the dot here. Now, there are different terminal states at the bottom. Now, if you've seen this enough, you probably know that the bottom is like fire pit. And you're probably going to get a big negative reward. And this thing is probably going to give you a positive reward. But Q-learning doesn't know that. So Q-learning cannot make that assumption. So we actually have to have the agent take steps in the environment, and then we can learn like what are those values that should be assigned to each state in action. So let's see what happens. All right. So you saw the agent went from here to here, but nothing changed. Like all of the numbers are 0. Why is that? It's Q-learning. So we got a transition when we went from here to here, and let's assume that we got no reward. So no instantaneous reward. So the only reward is like if you go to the bottom or this thing here. So if you get no reward, then the only thing that applied in the Q-learning update is, you have your reward plus gamma times the max over the action, then the Q for the successor state. But those were also zero because everything is zero here. So we get the Q-learning from that data tuple does not update the value. All right, same thing here. The agent went from here to here to here to here. It keeps getting zero reward. And the Q-learning update will say like the updated Q values are 0 plus gamma times 0. So that's 0. But now look at what happens here. So the agent is here. Then it'll go here. And then up. All right, so it went to here and then it exited. Now, whenever it exits, it gets a plus 10 reward. But Q-learning, if you remember the alpha, the alpha was 1/2 to make the math easier. Like usually alpha should be 0.001 or something, but to make the math easier, make it 1/2. So you get 5 here because what happened to you got instantaneous reward of 10 plus gamma times 0, which is 0, then that's 10, and then half of that is 5. And then you updated that with the Q value, which was 0 because we didn't know what it was originally, so it's 5. And then now look at what happened next. I think I'm gonna move to the same goal again. I just have to wait a little bit, yeah. All right. So it was over here, it moved here, and then it left. Now, when it was over here, and then it moved here, that was one transition, but the value went from 0 to 2.5. Yeah. If you printed the slide, I don't know if the numbers are high resolution enough to see. So why is it 2.5? Well, you're taking the average of 0 and 5. Because what happened is the agent was here, it moved here, it got no reward, but the successor state would give 5 for the Q value. So you get 0 plus 1/2 times 5, which is 2.5. And then you get 7.5 here because when you leave here, you get 10 reward plus what the instantaneous reward is 10, and then you have no other successor reward. So the instantaneous reward is 10, and then you're averaging it with the 5 that you've already gotten. Well, I shouldn't say averaging because what you're really doing is you're weighing 1/2 times 5 plus 1/2 times 10 because alpha is 1/2. Yeah. So look at what's happening here. So the agent keeps going right. All right. So it keeps going right, and then all the numbers here keep increasing. So, which makes sense because like after you've gotten more samples, it should converge to some reasonable reward. And especially if the discount is 1, which means there's no down weighting, then eventually all these numbers, they'll converge to like 10. But depend on what the discount factor is. So let's move forward a little bit. At some point, it's going to do something. Oh, there we go. So we thought that it was over here, then it went down. And so it got minus 100. But then because alpha is 1/2, we turn it to -50. So now it keeps going down, and then that keeps getting closer and closer to -100. So here's the question. So the agent had kept going right at the beginning, and then it kept going down here. But the Q value for this date, the Q value of the current date and then going right has stayed very high, like 9.4 here. It stayed very high, even though this is very bad. It's very important to know why. Because with Q learning, you can always assume that you take the max, and then when you take the max in that Q learning, like gamma times the max of all action that you can take in the successor state, then you effectively ignore this type of thing because you assume that, well, an optimal agent is going to be acting, no, is going to be taking this action instead of this one. That's why you'll see that all these that are like all these states and then moving right, they'll still have high value. And I think what's going to happen is they're going to go down. Oh, I guess not. It might be nice to explore some of these. All right. All right. Oh, so I guess they're only exploring this at the very end. Okay. Yeah. So did you have questions about how this operates? It's just like a grid road, except it's a different type, where we assume that the fire pit is like the bottom row, and then this is your like goal. So, all right, so Q learning has some amazing properties. All right, so Q learning can converge to an optimal policy, even if acting suboptimally. So we saw earlier that in that animation, you could send that agent down to the fire pit a lot and then keep getting negative reward. But the Q value themselves would still learn that it's optimal to just keep going right to get that reward. And so that will then result in what is the optimal policy, even if the behavioral or exploration policy is actually very bad. So that's what we call off-policy learning. So there's a lot of caveats, like you have to explore enough, you have to make the learning rate small enough, but not decrease it too quickly. But otherwise, it's very robust to action selection. Of course, you have to explore enough, like that theoretically, if you visit each state infinitely often, then the values that are learned from Q learning will become the true one. And then they'll converge to like, an optimal policy. But then you have to think about like, can you actually run it infinitely many, get infinitely many samples? I mean, if you're OpenAI, maybe, but not everyone can do that. All right, yeah. Oh, so the question is, how do you decide when to stop doing Q learning? Yeah, that's a good question. So I think the question is not like, when do you stop Q learning? I think your question is broader than that. When do you stop Q learning, or when do you stop reinforcement learning? It seems like Q learning is an example of a reinforcement learning algorithm. So how do you decide when to stop? Usually you observe the performance of the agent with reinforcement learning, and then have some curve that shows number of samples and then performance of the agent. And if it goes up and then levels off, then at some point, if it's leveling off and not improving, maybe it's time to stop. If the performance has kept increasing, then maybe you shouldn't stop. But deciding when to stop is not, there's no hard and fast rule for that. Uh, yeah. Hi. So far, when we have talked about Markov decision processes and reinforcement learning, we first talked about, like, let's assume we know everything about the Markov decision process. So the goal might be compute optimal values or compute optimal policy or evaluate a fixed policy. If you assume a model-based approach to trying to solve an MDP, then first get samples, approximate your model, and then do value iteration, policy iteration, whatever. If you don't know the if you don't know the model, if you don't compute it, then computing the optimal policy, use something like Q-learning. Which one is better or worse? I mean, depends on the task and depends on the, I guess the ideological views of who you're talking to. And yeah, we talked about recently model-free learning. So this means you experience the world through episodes. So you get state, action, reward, next state, next action, next reward, and so on. So usually I write the subscript like 1, then 2, then 3, like time step 1, 2, and 3, because otherwise you get too many primes here. But if you're only doing one transition tuple, then this is the commonly used notation: state, action, reward, next state. And this is like a flow chart if you want to, if that helps. And we just again, we've also again already talked about Q learning, so we would like to do Q value update to each Q state. Like, this is what we would like to do, but we're going to approximate this with samples instead. So you compute the average as you go, you get the sample transition. This sample will suggest that your approximate Q value would be the current reward plus gamma times the max overall A prime, which again, remember, is different from the A here. So you have like two different actions here. Then you want to average over the results from this, because it's only one sample. You could get many samples. And when you get more, usually your estimate will get better. And this is what we already saw an example of that. Like, this is the Q-learning update, like the one-time step Q-learning update. Step, any questions about this? And then, yeah, here's another video example. So this is just Q-learning running at random. So the policy, again, the behavioral policy that you see here, it's acting very bad. But the point is that even though it looks like it's behaving so bad, the actual Q values are going to end up converging to numbers that will give you the optimal policy. And then eventually you'll learn that if the agent is in here, going east has the highest value, so that's what the policy should be. And then same thing for the other state. So, and because this is a simulator, we can just run it a lot, and then we'll eventually visit each of these states like almost infinitely often. And we're not even we're only halfway through the video. Yeah. All right, see what happened here? So, like, again, we started from the case when the entire grid, there were all the estimates of the value were zero. And then over time, when the agent interacted with the environment, it got sampled, it updated the Q value, which means updating one of the numbers in each square. And with enough of those data points, you get updated value, then your optimal policy will result from that by taking the max action, the action that result in the max value for each grid component. And last thing for today is that when we were looking at that video, we didn't talk about how should the agent decide which state to go to. And that decision is also very fundamental. It relates to the exploration versus exploitation trade-off. So you can think of exploitation as, you have lunch or dinner, you have a usual place to go to, you like it a lot, but then there's a grand opening, and then you don't know if you should go there or not. So like if you like, well, I don't know, like what's the usual place that you like going to? Nobody goes to food places on campus to eat, or what's the usual place? McDonald's? Oh, I haven't been to McDonald's since 20, maybe on the order of 20 to 25 years since the last time I've been to a McDonald's. But let's say that's your favorite place. I'm telling the truth, I think, yeah. So you have your usual place, but then there's another restaurant that opens up. Then you might want to think, well, maybe I should try that. Because unless you try that, then unless you explore that, then you don't know if it will eventually be better. So. All right, so how do you explore? So there are some very simple schemes. So one of them is epsilon greedy. Every time step, you flip a coin, and with, well, I guess you don't have to worry about flipping a coin. I guess this is just like for like, intuition, but just think of it as, you have your agent, your decision making, like which restaurant to go to, and then with some small probability epsilon, you just make a decision randomly across all the possible things you could do. With large probability, 1 minus epsilon, you act according to your current policy, which one is the best for you. Usually, I mean, depends on your current policy, but usually your current policy is like what's going to be the best for you. But of course, the problem is that when you're doing exploration randomly, like even though like random exploration is actually very effective and widely used, then you eventually explore the state space, but it's sort of like you keep thrashing around. So there's no like, it's not really a principled way to explore the state space. And the way that people get around that is by using exploration functions to give a more principled like way of going to states that have not whose like badness has not been established yet. And this is like another demonstration. So this is a different grid world. Like again, you can probably guess that there are danger fire pits in the top row and the bottom row. And then this is manual exploration. So someone is just clicking button and then like guiding the agent to go somewhere. So if the agent is here and move there, I think the video should make it move there. It gets +1 reward, then +1, then +1. So this is like your McDonald's, like you get your normal reward every time you go there. But if you don't explore this other region, then you don't know if something's going to be much better. So this is, this is why exploration has the potential to uncover a lot higher value region in the environment. And then what should happen next is the agent or the human controlling it should make the agent move to the right to see what will happen. Yeah, then I see, yeah, so it moved down check it, it tries it a few times, check to make sure that it's very bad, and then it establishes that it's a bad state. Now it explored a little bit, and then it sees, oh, it got a high reward, so let's keep exploring in that region. And we see that it does get much higher values, though that, in the long run, this agent will do better than one that just stuck with moving to the left, but then only getting +1. And of course, you do have to keep exploring other regions. Like it could be the case that other, components actually do give a lot reward, but you never know until you try that. Yeah. So when to explore? So yeah, we talked about like random exploration, but then the idea would be explore areas whose badness is not yet established. Once you go there, see that it's bad, maybe just stop going there, and then try different regions of the state space, or try different actions that will lead to different regions. So a very naive way of doing that is, you have our value estimate, and then you base it on like visit count. So if you can enumerate all the states, then you can keep a count of how many times did you visit a given state? If you've only visited it like once or twice, then maybe you should go there again to keep checking to make sure that you didn't miss something very valuable. But if you've already been there 100, 1,000 times, and you see that's very bad, maybe just spend your time somewhere else. That's basically what's going on here. You can modify your queue update so that instead of just using queue, you can do this function, which is like this u is like your q value. So your value plus k over n, like k is some arbitrary constant. Think of it as like 1. N is based on the number of times that we visited. It really should be n plus 1 to avoid division by 0. But as you visit this state more and more often, this component goes to 0. But if you've only visited a few times, then you get a big bonus because you want the Q value to reflect that, it's going to be higher value to go in to take this action because it's going to lead you to a state that you haven't, that you don't really know what value it is yet. Then this will propagate the bonus, back to state that lead to the unknown state as well. So yeah, that's the exploration function. I mean, in practice, humans don't do the calculation, but if you're programming an AI agent, then many people have explored different ways of defining and arguing that this exploration function is better than this other exploration function because it helps increase like the state coverage that has been visited. Question? So we covered a lot today. So in summary, we covered reinforcement learning. So we talked about model 3 and model base. So we actually covered model base first. So sorry about that. Next week, we'll talk more about imitation learning, which is probably simpler than reinforcement learning. So we'll cover that, and then we'll cover dynamics. And then after that, we'll cover more advanced and special topics. By advanced, I don't mean it's too mathematically advanced. I just mean it's more exciting because it's like cutting edge research. All right, I'll see you next week. Yeah.